In this video, we will look at worksheet 7C on bond and molecular polarity. And to complete this worksheet, in addition to the worksheet itself, you will also need a periodic table that has electronegativity values on it, which you can get up front in the classroom or you can look up one online. So to start this activity, we are looking to determine whether each type of bond is polar, nonpolar, or whether it is actually an ionic bond that will form. And we're going to start by calculating the difference in the electronegativities for each pair of elements, and then we will put them in categories, and after we do that we will draw a picture of the bond polarity. So as you can see, the first one is done for us. So we have sodium and chlorine. So the electronegativity of sodium, element 1, is 0.9, and apparently the person who did the example, their electronegativity periodic table showed 2 decimal places, whereas ours only shows 1. But that's okay, it doesn't really matter because we're just looking at the trend. So 0.93, and then chlorine has an electronegativity, chlorine of 3.0 or 3.16 on this periodic table. And so the difference is about 2, which if we look at our chart up here, if it's greater than about 2 or 2.1, it is classified as an ionic bond. And the other way we can know that this is ionic is because sodium is a metal, and things that contain metals are pretty much always ionic. The metal is going to give up its electrons to the non-metal that wants the electrons. And we show the bonds of ionic things with separate charges. So we show a positive on one end and then a negative on the other end. And since sodium and chlorine both have charges with an absolute value of 1, we can just show it as a plus and a minus sign. Or of course we could also show +1 and -1 if we wanted to put the values of the charges on there. Without the 1, remember that 1 is implied. So let's move on to number 2. We have germanium, Ge, which if we look at the periodic table is right here with electronegativity of 1.8. So I'm going to go ahead and put 1.8. And then fluorine, which has an electronegativity of 4.0. It's the most electronegative element on the periodic table. So if we take the difference between those numbers, we get an electronegativity difference of 2.2. So judging by this is going to be an ionic bond. And then we can show our separation of charges. And so if we have an electronegativity difference of 2.2, which based on our chart that would be an ionic bond, but germanium is not a metal. It is a metalloid. And so we know that it can't be an ionic bond, it is just an extremely polar covalent bond. So I'm going to put polar covalent. And since this is covalently bonded, it is an extremely polar bond, but it is covalent, so we're not going to show full charges, we're just going to show partial charges with these weird looking S things. So we have G, E, and F, and we are going to show a partial positive and partial negative. So fluorine is going to attract more of the electron density, so it's going to have a partial negative charge, and germanium will have a partial positive charge. Then we have carbon and hydrogen. So carbon is 2.5 on the electronegativity table, and hydrogen is 2.1. So we have 2.5 and 2.1 with a difference of only 0.4. And so this is relatively nonpolar. Nonpolar. It's within that range of nonpolar covalent bonds. So we are going to put carbon bonded with hydrogen, and we're not going to put any partial charges because this is a nonpolar bond. let's see, moving the paper up. And now we have oxygen bonded with oxygen. So we can look up that value. A value for oxygen is 3.5, 3.5, and 3.5. But the electronegativity difference is 0 because they're the same exact atom. So this is clearly going to be a nonpolar bond. The two oxygen atoms are going to share electrons exactly equally. So we have oxygen bonded to oxygen. Now this wouldn't actually be a single bond, but I'll let you figure out the Lewis structure later. And because they share electrons equally, we don't show any partial charges. Next we have barium. Barium is all the way down here with an electronegativity value of 0.9. 0.9. And then we have bromine with an electronegativity value of 2.8. 2.8. So we have a difference of 1.9 here, which puts us pretty far into the polar covalent range. So out of barium and bromine, bromine is the partial negative charge. So we put partial negative on bromine and then partial positive on barium. Next up we have lithium and nitrogen. Lithium is 1.0 and nitrogen is 3.0. Lithium 1.0 and 3.0, which is a difference of 2.0. So this is very polar, and also lithium is a metal, so this is going to be an ionic bond. We are going to have a complete transfer of electrons and full separation of charge. So we have lithium bonded to nitrogen. Lithium has a +1 charge, and nitrogen actually will have a -3 charge. So we'll show both those charges on the ions in the ionic bond. Next we have carbon and bromine. So carbon, we already looked up, has a value of 2.5 for electronegativity. And bromine, we also looked up right here, has a value of 2.8. So if we subtract that, we get 0.3. So this is a relatively nonpolar bond. Now remember, this is a scale. There's not to say that carbon and bromine, it's not to say the bond between them isn't polar at all, but it's relatively nonpolar. It's much less polar than, say, the bond between carbon and oxygen. So we will show carbon bonded to bromine, and because we're classifying this as nonpolar, we won't show any partial charges. Although in some cases, this molecule may be polar enough to do things like dissolve in water. That polarity is a scale, it's not a really set cutoff point. These are just guidelines for classification. Next we have arsenic and chlorine. So arsenic is 2.0 and chlorine is 3.0. So 2.0 and 3.0, which is a difference of 1. And so that puts us in the polar covalent category. Valent. Arsenic and chlorine, with chlorine getting a partial negative charge and arsenic getting the partial positive charge. Then we have nitrogen and nitrogen. Nitrogen's 3.0. 3.0 and 3.0 gives us a difference of 0, meaning that this is fully nonpolar. And then we're going to show our bond, which once again is not a single bond, but just go back and try and draw the Lewis structure yourself. And then last but not least, we have silicon and hydrogen. So silicon is 1.8, hydrogen is 2.1. 1.8, 2.1, which is a difference of 0.3, which is relatively nonpolar. So silicon and hydrogen is a nonpolar bond. Now on the back of this sheet we are going to look at polarity of the molecule, and the first one is done for us. So we have HOCl, and we said this molecule is a bent molecule. And so one of the bonds is polar and the other is nonpolar, but because of this asymmetry, we resulted in a molecule that is polar. This next one, we have HBr, and that is a linear molecule, meaning it will all be in a straight line. So we just kind of need to determine if this bond is polar. So HBr, we have bromine with an electronegativity of 2.8, and hydrogen with an electronegativity of 2.1, which is a difference of 0.7, which makes this a polar bond. And since there's only one bond in the molecule, then the molecule must also be polar. Next we have H2O, which is water, and we know that water is a bent molecule. And that OH bond is a polar bond. We have one with an electronegativity of 3.5 and hydrogen with 2.1. So that's definitely a very polar bond. If this molecule is linear, then those polarities would cancel each other out. We'd have something that looked like this, with hydrogens on either side. Our arrows would point in at one another and they would cancel out. But because water is a bent molecule, we have electron density traveling in general in the same direction, which results in an overall polar molecule, with the electron density being drawn up towards the oxygen. So this is a polar molecule. Next we have pH3, which is a trigonal pyramidal model. It looks sort of like this, with one thing in the middle, and then we have 3 atoms off the bottom, and then we have our lone pair at the top. But this pH bond, phosphorus with 2.1 and hydrogen with 2.1, is a nonpolar bond. And since that's the only type of bond we have, all the bonds are nonpolar, making the molecule also nonpolar. To have a polar molecule, we have to have at least one polar, or to have a polar molecule, we have to have at least one polar bond. Next we have CH4, and those CH bonds with carbon 2.5 and hydrogen 2.1, these are also relatively non-polar bonds. And also, even if you thought they were polar, if you draw your arrows all pointing in towards carbon, then you'll notice that all the arrows cancel out anyway. So this is a non-polar molecule. Then we have N2, which is linear, and because these are the same atom, we can go ahead and say that bond is going to be nonpolar, and the molecule is going to be nonpolar as well. Then we have sort of a tricky one down here. We have something that has more than one atom in the middle. We have carbon and then we have nitrogen in the middle with hydrogens connected to both of them. So we know that that carbon-hydrogen bond is going to be nonpolar, because we've already discussed that. But what about the nitrogen-hydrogen bond? What about that bond? Nitrogen is 3.0 and hydrogen is 2.1. So that bond is actually polar. So what does that mean for our overall molecular polarity? Well, all these bonds are relatively nonpolar, but let's go ahead and draw the arrows anyway, because they do have some difference in electronegativity. So if we were to draw these arrows, they would all point in towards carbon. But then between carbon and nitrogen, carbon is 2.5 and nitrogen's 3.0, so these electrons are being drawn towards the nitrogen. And then also with the hydrogens, the electron density is being drawn towards the nitrogen. So overall, this molecule does have a polarity. The electrons are being drawn towards the nitrogen. So overall, this is a polar molecule. Next we have COH2, and we have carbon-hydrogen bonds, which we know are relatively nonpolar. And then we have a carbon-oxygen double bond. where carbon has an electronegativity of 2.5, oxygen is actually 3.5. So this is a difference of 1, making this a polar bond. So our electron density is going to be drawn up towards the oxygen. So this is going to be a polar molecule because our arrows are not symmetrical. There's nothing to cancel out this oxygen drawing the electrons upward. It's a polar molecule because of that. Then we have C2H2. The carbon-carbon triple bond is going to be nonpolar because it's 2 of the same atoms. And then the carbon-hydrogen bond is also going to be nonpolar. Plus, this molecule is completely symmetrical. So this molecule is definitely going to be nonpolar. Then we have CH3Cl, carbon-hydrogen bonds. Those are nonpolar. And then our carbon-chlorine bond, looking at that, carbon is an electronegativity of 2.5 and chlorine is 3.0, which makes this a polar bond, with the electrons being drawn up towards the chlorine. So overall, this molecule is polar. And you can see that even better if you draw this with its correct orientation, with all the hydrogens going down in its tetrahedral shape and the chlorines going up. All that electron density is being pulled up towards chlorine, making it polar. Then we have CO2H2. We have several types of bonds here. We have our carbon-oxygen bond, carbon-oxygen single bond, which is a polar bond. We have a carbon-oxygen double bond, which is also a polar bond. We have an OH bond, which is polar. And we have a carbon-hydrogen bond, which is nonpolar. So we have to draw our arrows here and figure out whether we have symmetrical electron distribution or not. So our arrow is going to be up towards the oxygen, and then here out towards the oxygen. And then here in towards the oxygen. So we have a lot of arrows, but they are not symmetrical. So this molecule is going to be polar. Then we have HCN, or cyanic acid. So we have our CN bond with triple bond, carbon being 2.5, and nitrogen being 3.0, so this is a polar bond. And then we have H and C, which we know is a nonpolar bond. But since the electron density is being drawn towards the nitrogen, this will be a polar molecule. So in this last one, we have an oxygen-oxygen bond, which is nonpolar, an oxygen-hydrogen bond, which is polar. And so we draw our arrows, and in general they point up towards the oxygens. If this were linear, those arrows would cancel out, but it's not a linear molecule, it is bent. So in general, our electron density is being pulled upwards towards the oxygens, making this a polar molecule.